Hey guys, how you doing? This is Mr. Lee. This is our first video for Chapter 8. So Chapter 8 has two sections, the binomial distribution and the geometric distribution. And in today's video, we're going to cover part of 8.1. We're not going to get through all of it, but we're going to get through part of it as much as we can. So in 8.1, you're going to determine whether the conditions for binomial settings are met. So you're going to check your bins, B-I-N-S. Geometric, you're going to check your bits, B-I-T-S. Okay, those are two acronyms. You're going to compute and interpret probabilities involving binomial random variables. You're going to calculate the mean and standard deviation of a binomial random variable and interpret these values in context. And then you're also going to calculate probabilities involving geometric random variables. Okay. We're probably only going to get to these first two in this first video, and then I'll either be back with you in person or I'll have to make another video. Okay, so the very first thing we want to start with is checking whether we are in a binomial setting. So you'll be given some kind of contextual information, and you have to determine whether or not that qualifies as a binomial setting. Okay, so the word binomial, so meal means obviously like numbers, and bino or bine, okay, bi means two. Okay, so are we in like a two numerical, setting? So what is a binomial setting? So when the same chance process is repeated many times, we want to know whether an outcome happens or doesn't happen. So it's either a yes or a no. So this is like a binary thing. It's either 0 or 1, true or false, yes or no, success or failure. Okay. And in some cases, the number of repeated trials is fixed in advance, and we are interested in the number of times a particular event occurs. And that particular event, we're going to call a success. Now, success is not a qualitative term. It doesn't mean good or bad. Success is just whatever we define it as. So, for example, like if we're flipping a coin, we can call a success a head, or we could call a success a tail. It doesn't matter. So even though we're calling something a success and a failure, it's not like a quantitative or even a qualitative term. Okay, but we have to define what the success is. So if the trials in these cases are independent and each success has an equal chance of occurring, we have a binomial setting. So here are actually, like, within this definition of a binomial setting are all the conditions that qualify something to be a particular scenario to be a binomial setting. Okay, so we have a little acronym BINS, B-I-N-S, to summarize these four things. Okay, so a binomial setting arises when we perform several independent trials of the same chance process and record the number of times that a success occurs or that a particular outcome occurs. Here's the four conditions. Binary. First of all, is there only two possible outcomes? Okay, and there can't be many different outcomes. Can we classify the outcomes as just a success or a failure? Okay, so are we in a binary setting? I is for independent. The trials must be independent of one another. That is, knowing the results of one trial must not have any effect on the results of another trial. Okay, and we learned 2 chapters ago about independence. The probability of A is equal to the probability of A given that B has already occurred. Okay, so that's how you check if two things are independent, but all of these trials have to be independent. So as we're doing the trials, it doesn't impact the probability of success for the later trials. Okay. Now, in reality, sometimes we have a pseudo-independent, not exactly independent setting. Okay. But if the situation is large enough, so for example, if we have a deck of cards, okay, and we're sampling without replacement, so we take a card out, but we don't replace it. Okay. And let's say that we're going to define success as we get a heart. Okay, so are those trials independent? Like if you take one card at a time out of the deck without replacing it, is there independence? Well, of course there's not independence, because if you take one card out, okay, and then you don't replace it, then the probability of success for that first card would be 13 out of 52. But when you toss that card aside, the probability of success for the next card is not going to be 13 out of 52. It's going to be something out of 51, depending on whether or not that first card was a success. Then you take that second card out, that third card is out of 50, that fourth card is out of 49. So you can see that the probabilities are changing, and so these are not independent trials. But what I'm talking about is, let's say you had a million decks of cards, okay? And so now, instead of, and you're still sampling without replacement, and you take one card out, and the probability of success is, 13 million out of 52 million, okay? And then you take that card out, and then you take the next card, and that probability of success could be 13 million out of not 52 million, but 51,999,999. Okay, so the probabilities are slightly different, but the difference is so minuscule that sometimes we kind of let it slide. Okay, and we say, okay, well, we're not exactly in an independent setting, but we're very close. Okay, but it would have to be a pretty large setting. Okay. Okay, and then number. Is the number of trials fixed in advance before you start taking the cards out? Okay, you have to fix that. Okay, I'm going to do n number of trials. Okay, I'm not going to just like start and then just stop whenever I want. Okay, before I even start, okay, is the number of trials fixed in advance? Okay, it has to be. And then finally, S is, do we have the same probability of success? The same probability of success for each trial. So the probability of success does not change. Okay, and by the way, the number of trials is little n, just like sample size, right? And then the probability of success, we use little p. And something that's not in your textbook is if we're in a binary setting, so it can, each trial the outcome can only be a success or failure. Okay, so if the probability of success is p, what's the probability of failure? It's a binary setting, so it's 1 minus p, right? Well, that part is in your textbook, but what isn't in your textbook is sometimes we call the probability of failure q, little q, okay? So we have little n, little p, and little q. So go ahead and write that in your notes. Little q is the probability of failure, which is equal to, it's just the complement of the probability of success. So little q equals 1 minus p because we're in a binary setting, okay? So check your bins, B-I-N-S. Now later in a geometric setting, we're going to check our bits, B-I-T-S, okay? But we're going to spend a lot of time in Chapter 8 talking about the binomial setting and then not as much time about the geometric setting. But once you fully understand the binomial setting, the geometric setting is actually super easy. Okay, there's some calculator functions that go along with this section, and we'll talk about that. And there's some math, but again, they've taken the really heavy math out of it, but there is some light math that you do have to remember. There is actually a little bit of combinatorics and a little bit of algebra involved in here. You have to remember what a factorial is. If you don't worry, I'll tell you about it. Okay, so check your bins. And that's how you tell if something is a binomial setting. So let's check this out. Let's consider tossing a coin n number of times. So we're fixing in advance that we're going to toss it n number of times. We don't just start tossing and tossing and tossing until we feel like, not tossing anymore. Okay, so we fix the number of trials, a little n, in advance. Each toss is either going to be a head or a tail. And knowing the outcome of one toss does not change the probability of an outcome of any other toss. And then if we're just going to define heads as a success, then little p, the probability of success, is 0.5 for any individual toss. And that does not change. So the question is this a binomial setting? Well, bins, check your bins. B, binary. Is there only two possible outcomes, success and failure? Yeah, head and tail. And we define head as success, tail as failure. Okay. I, are trials independent of one another? Yes, they are. N, are the number of trials set in advance before we start, doing the trials? Yes, we are going to do it n number of times. Okay, and then S is the probability of success, the same, S is for same. Is it the same for every single trial? Yes, it's 0.5. Okay, so the number of heads in n tosses is a binomial random variable x. Okay, the probability distribution of x is called a binomial distribution. Because we're in a binomial setting, we know that x is a binomial variable, binomial random variable. Okay, so let's go ahead and define this. The count x of successes in a binomial setting is a binomial random variable. The probability distribution of x is just the binomial distribution with parameters n and p. And also remember there's q, but q is just 1 minus p. Okay, so we can just limit it to n and p. N is number of trials, and p is probability of success for each individual trial. Okay, the possible values of x are the whole numbers from 0 to n. So now when checking the binomial condition, when checking your bins, be sure to check the bins and make sure you're being asked to count the number of successes in a certain number of trials. Okay. All right, so here's our example. Okay, so in a binomial setting, we can define random variables, let's say x, as a number of successes in n independent trials. We're interested in finding the probability distribution of x. So let's look at probability distributions first of all. Okay, so here's our example. So we have this nice family, and we want to look at something about blood type. Okay, so each child of a particular pair of parents has probability 0.25 of having type O blood. Genetics say that genetics say that children receive genes from both or each of their parents independently. Okay, if these parents have 5 children, the count x of children with type O blood is a binomial random variable with n equals 5 trials. So each one of the kids is a different independent trial, and probability of success is 0.25 for each one of them individually to have type O blood. Okay, and they're independent. Okay, number of trials is set in advance, and the probability does not change. Okay, in this setting, a child with type O blood is called a success, and a child with another blood type is, we're just going to call that a not success or a failure. What is the probability that x is exactly equal to 2? So in this context, what does this mean? Contextualized, what does this mean? This is the probability that exactly 2 of their children have type O blood. Well, this x equals 2 can happen a number of different ways, right? And now you have to think of the different combinations. Out of 5 kids, how many different ways can you have 2 successes? Okay. So here is the probability of exactly 2 successes, S, S, F, F, F. So S is for success, F is for fail. Okay, so the probability of success, fail, fail, fail is 0.25, 0.25 times 0.75 times 0.75 times 0.75, or 0.25 squared, or raised to the 2 power, okay, because that's how many successes there are, is the probability of success raised to the power of 2, and then the probability of fail raised to the number of how many fails we have, okay, and that is equal to 0.022637. Okay, but there are different combinations in which you can have 2 out of 5 children having type O blood. You could have oldest, youngest, oldest, middle, oldest, blah, 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 right? So how many different combinations are there? Well, here they are right here. Okay, so verify that in each arrangement, probability of x is equal to 0.02637. So these are all the different ways in which you can have 2 successes out of 5, right? So 5 choose 2. So therefore, the probability, there's 10 different ways. So now you have to multiply these 10 different ways times the probability of 1 success, which the probability of 1 success is 0.02. So the probability of multiplying this by 10, because there's 10 successes, 10 different ways you could have successes, you get 0.2637. Okay, so the probability that exactly 2 out of 5 children will have type O blood is 0.2637. So in the previous example, any one of those arrangements of two S's and three F's has the exact same probability, right? 0.02, whatever it was, 637. This is true because no matter what arrangement, we'd multiply 0.25 twice and 0.75 three times. So we can generalize this, and now we have a formula, okay, for what is called the binomial coefficient. The binomial coefficient, okay? And the binomial coefficient, you've probably been introduced to this in Algebra 2, especially if you took Advanced Algebra 2. Okay, the binomial coefficient is just n choose k, right? Where k is the number of successes in n trials or in n observations. Okay, so this is the notation for n choose k. This is another notation. This is a different notation for n choose k. This is combinations. And then what does this actually equal, like mathematically? How do you figure out how many different combinations of 2 you can pull from 5? Okay, well, it's just n factorial over, remember, k is the successes, k factorial times the failures factorial. Okay. Now, do you have to memorize this? No, because I mean, it's nice to memorize this, and you probably already know this from Advanced Algebra 2 or maybe pre-calculus. Okay, but we're not going to do these by hand. Okay, we're going to be using technology. We're going to be using the TI-83 or the TI-84 to calculate combinations. And the shortcut for this entire thing is found in, if you just turn your calculator on, okay, let's say we want to do 5 choose 2. Okay, so what you type in your calculator is punch in 5. Okay, so you're going to put this number first, 5, and then for the combinations or for the choose, you're going to go math, scroll over to PRB, probability, scroll down to combinations, and CR. Okay, so go ahead and press enter. When you're hovering over 3, press enter. So now on your calculator, it shows 5 NCR, and now you have to put in, well, how many successes do you want to have, or how many successes are you looking for? 2. So 5 NCR 2, press enter, and you're going to see that it's just 10, right? You can also do this, if you don't believe me, you can do this the long way. Okay, you can do n factorial over k factorial over n minus k factorial. So what would this be? What would this be? Think about that for a moment. So n is 5. So this is 5 times 4 times 3 times 2 times 1. Okay, k, how many successes? 2. So that's 2 times 1. And then n minus k, how many fails? 3. So it's 3 times 2 times 1. Okay, so you can do the math there. It's actually very simple math. You just cross out a whole bunch of things, right? Okay. Always remember with factorial, 0 factorial is always equal to 1. Okay, that's just a rule. You just have to memorize that. Okay, so now here is the binomial probability. Okay, here's the formula for the binomial probability, right? So in that last example where we had 5 choose 2, the typo blood, okay, we write this statement as probability that x is your random variable, x is equal to little k. Little k is just how many successes. So this would be probability that x equals 2 in that last example with typo blood, right? So the probability that x equals k, just to generalize, that x equals k, remember that's number of successes, is equal to, okay, now here's your binomial coefficient, n choose k, okay, and then now you have p, little p is the probability of success, which in the typo blood, they will tell you what that is. That was 0.25 raised to the k power. In that last example, it was raised to the 2 power times, this is q. Remember I told you that 1 minus p is just the same thing as q. So this was 0.75 raised to the 3 power, right? Because that's how many fails we have, was we had 3 fails, we had 2 successes, but there's 10 different ways, or 5 choose 2 different ways that this arrangement can happen. Okay. Okay, So if X has the binomial distribution, N is the number of trials, okay, this is a formula worth memorizing, okay, and having in your notes. Okay, so each child of a particular pair of parents has probability of 0.25 of having type O blood. Suppose the parents have 5 children. A, find the probability that now exactly 3 of the children have type O blood. Exactly 3. Okay, so we can just use this formula, right? So what's the probability that X equals 3? Okay, so we're looking for that one unique probability, X equals 3. Well, what was N and what was K? N was 5. K is now 3. We defined it as 3. Probability of success is 0.25 to the 3 power. Okay, and that is times 0.75 to the 2 power. Okay, so here it is right here. Probability that X equals 3. 5 choose 3. 0.25 to the 3rd power. That's how many successes, because now we're looking for 3, exactly 3. And then 0.75, that's how many fails we have. So this is your probability. Okay, so your probability that exactly 3 children have type O blood, well, it went down a lot, didn't it? Because the probability that 2 children was like 26% or something like that, right? 0.26 or something like that. And this is only like 8%, so a little more than 8%. So 0.08789. So what if the parents have more than 3 children that have type O blood? Well, what does more than 3 mean? It means 4 or 5, because remember, the number of trials is set at 5. They determined we're going to have 5 children. Okay, they determined that in advance. Okay, so N equals 5. So they want to know, so you have to add now the probability that X equals 4 or plus the probability that X equals 5. Okay, so you can just hammer these out with the binomial probability formula, and then just add those two formulas together, right? And what we find is there's only about a 1.5% chance that more than 3 out of 5 children would have type O blood. Yes, the parents would be surprised, okay, if they had more than 3 children out of 5 have type O blood. Yeah, that'd be surprising to them. Okay, so now we're going to look at the mean and the standard deviation of an entire binomial distribution. Okay, so we describe the probability distribution of binomial random variable just like any other distribution by looking at the shape, center, and spread. Consider the probability of distribution that X is equal to the number of children with type O blood in a family with 5 children. Okay, so here's your different X's. So 0, 1, 2, 3, 4, 5. Those are the different outcomes that could occur. Here's the associated probability of each one of these. Okay. And you might be looking at the probability of 1 and going, well, wait a second, shouldn't that just be 0.25? No, because there's 5 choose 1. There's 5 different ways that this could actually happen. It could be the youngest child, the oldest child, one of the, so it's not just 0.25. Okay, so here are the associated probabilities, and remember, how do you check if this is is an actual probability distribution? Each one of these has to be a legitimate probability, which they are. These all have to add up to 1, which they will. Okay. So where is the center of this thing? Well, the center is just the mean. We're just going to talk about the mean or the expected value. Well, let's not talk about expected value. Let's talk about the mean. Okay, so the mean of this thing is just exactly the mean of any other random variable. This times that plus 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 this times that. And when you do that, you find that the mean is 1.25. So if I'm having 5 children, my expected value, or the mean, I would expect about 1.25 of those children to have type O blood. Okay. Well, what is the spread? Well, let's talk about the variance. How do we calculate variance? Variance is just take each one of these, subtract it from this mean, square that difference, then multiply it by its associated probability, and do that for all of them. And then that's the variance, and then the standard deviation is just the square root of the variance So our variant or our standard deviation of x is about 0.968. The shape. Okay, you can see that this probability distribution is skewed to the right. It's more likely to have 0 or 1, okay, children, or 0, 1, or 2 children than it is to have 3 or 4 or 5 children with type O blood. Okay. All right, the last thing we're going to talk about in this video is Binomial PDF. Binomial PDF. So this is a calculator shortcut. So go ahead and turn on your calculator. Let's go back to this probability right here. Okay, probability that x equals 4. Okay, this is a probability density function, PDF, binomial PDF. So we want one particular point. Okay, so binomial PDF is the probability density function, and we're going to calculate that. So turn your calculator on, go to second vars, which is all your different distributions. Scroll all the way down, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, A. A. A is binomial PDF. Go ahead and select that. Okay, what was the number of trials? Your calculator is asking you for trials. That's N. Okay, so there's 5 trials. What's the fixed probability of success for each trial? Little p, that's 0.25. Then what is the x value? So your calculator calls it the x value, okay? And you can also think of it as k, the success, or the x equals 4. So we want to know what's the x value of 4. Go ahead and paste that, press enter, and what do you get? 0.0146484,375. Or if you look right down here, sorry, I just blocked it because I pointed down there. Same thing, rounded off though, right? 0.01465. Okay, let's do the same thing for probability of x equals 5. Let's see if you can do it on your own. Pause the video, do it on your own. Okay. All right, so you're gonna push second vars, which is all your distributions, scroll down, or you can scroll upwards, okay, and skip Geomet PDF, plus all PDF. Go all the way up to A, the binomial PDF, 5.25, and now the x value is 5. Paste and enter, and you get 9.76567 or 625 times e to the negative 4, or times 10 to the negative 4. So what does that mean? That just means that 9 is the 4th decimal place. Okay, it's the 4th place after the decimal. So there's 3 zeros in front of it. And you can see down at the bottom of my screen, 0.000, there's 3 zeros, 0.0009, and then they round it off to 8, which is fine. Okay. Now, there's also the cumulative density function. Remember, with normal CDF, we never use normal PDF. We only use normal CDF. Well, here, we are using PDFs, okay, but we can also use binomial CDF, the cumulative density function. And remember, with normal CDF, it gave us the left tail. It gave us from a maximum value and everything to the left of it, just like table A did, right? It was always a left tail. Well, binomial CDF is also a left tail. Problem is, this is a right tail question, isn't it? The probability that x is greater than 3, well, that is a right tail question, right? Because x equals 4 is the minimum, and then it goes all the way, it finishes the distribution. So how can you turn this into less than? Okay, pause the video and think about that. See if you can figure it out. Okay, so this is going to be, okay, because remember that x equals 0 plus x equals 1 plus x equals 2 plus x equals 3 plus x equals 4 plus x equals 5. That's the entire probability distribution. So those probabilities all add up to 1. So just using the complement rule, if we're looking for x equals 4 plus x equals 5, that's going to be just the complement of x equals 0 plus x equals 1 plus x equals 2 plus x equals 3, right? So 1 minus the probability that x equals 0 plus blah, 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 blah. Okay, and there is your binomial CDF. Okay, so second vars, Scroll down to B now, binom CDF. Number of trials is 5. Okay, probability, the fixed probability of success is 0.25. Okay, and then your X value is what? What is your X value now? Remember that CDF, it's a left tail. So your X value is going to be 3. Go ahead and paste and enter and get 0.984375. Then just do 1 minus second answer, and you get 0.015625. Okay. All right, guys, hope you enjoyed the video. That's all I have for now. We'll finish 8.1 and talk about 8.2 in the next video or when we get together in person. Thanks. Bye-bye.